Good morning, class. We are looking at chapter 3, derivatives, and here's section 3.3, basic differentiation formulas. We looked at derivatives and rates of change, the derivative as a function, and now the basic differentiation formulas. Some of them are here. We're going to discuss them with more details as we go through examples. d dx of c is 0. That means a constant results in 0. d dx of x to the power of n is n x to the power of n minus 1. This is called the power rule. d dx of e to the power of x is e to the power of x itself. d dx of sine of x is cosine, and the derivative of cosine is negative sine. Reminding everyone of what we have done as far as having 2 points, calculating the slope. This format, f of x minus f of a over x minus a. This format, f of a plus h minus f of a over h. So it depends on the format that you have. And if you call the second point b, f of b minus f of a over b minus a. Not a big deal. However, to find the slope of a tangent line is a big deal because you have only 1 point. So what do? We move the secant line, PQ, closer and closer to the tangent line. The tangent line will be the limiting position of the secant line, PQ. And with that being the case, it gives rise to the definition of its slope, the limit of m of PQ as Q approaches P. If you look at this one, the limit of f of x minus f of a over x minus a as x approaches a. If you look at this one, the same limit as h approaches 0, the limit of f of a plus h minus f of a over h as h approaches 0. And so we call that the slope of a tangent line, or f prime at a, and these are various forms of a line. If you use the point slope for that point, you end up with y minus f of a equals f prime of a times x minus a as the equation of a tangent line. However, no need to memorize that. Stick with this. And in general, f prime of a becomes f prime of x, or the derivative function f prime of x is limit of f of x plus h minus f of x over h as h approaches 0. And now the basic differentiation formulas. Let's start with a constant. F of x equals c. That means f of x over y equals a number. As you know, that's a horizontal line. And the slope of any horizontal line is 0. So the fact that we know that, it's a proof f prime of x is 0. On the other hand, if you want to go by the definition, f of x plus h, because this is a constant, f of x plus h, or f of x, or f of any number for that matter, f of 10, it remains at c. Now, c minus c over h. C minus c is 0. Remember, h is approaching 0. It's not precisely 0. It's very close to 0. And so 0 over h is 0. And that means the derivative of a constant function, d dx of c, is 0. Any number. We remember the compound interest. And remind you the simple interest was PRT. I equals PRT, the principal times the rate times the time. Compound interest, A equals P times 1 plus R over N to the power of N. TP is the principal, R is the rate, times the time, just as here in years. N is the number of compounding that takes place in a year. A is the total amount. That means, in essence, over here would be P plus I. That's what A is in one shot. Now, if we represent R over N as 1 over M, its reciprocal is M, and the product, the cross product here results in this. And so we can replace the N with R times M. So we are going to replace R over N with 1 over M. And we're going to replace the N with Rm. This is what we did in algebra, okay? And so 1 plus R over N becomes 1 plus 1 over M. n becomes m times r or r times m. We put the m here, rt outside. And as you recall, this is compound interest continuously with e to the power of rt in this format, meaning if you let this go to infinity, compounded continuously. Okay, that's what happens here. It's important to understand this is becoming that if you let this repeats itself as far as n going to infinity. With that being the case, this limit, this expression, the limit as m goes to infinity. Now, 1 over m, if we let it be a variable x, y, z, h, then m is 1 over h. So I can replace the 1 over m with h, m with 1 over h. So if m is approaching infinity, 1 over m is approaching 0, h is approaching 0. So I hope you recognize these two are just the same with this manipulation we did here. And it's about 2.71828, and it continues indefinitely, and that's important to know. So E has this definition that we have seen in algebra, limit of 1 plus 1 over n to the power of n as n approaches infinity. By the way, as long as these three are the same, it's the same. You can say x, y. These three variables must be the same. If you go with this, these three variables must be the same. And this is another one. E is such a number that the limit of e to the power of h minus 1 over h as h approaches 0 is equal to 1. And we will look at the proof of that later. All right, what we want to do here, everybody, we want to remind everybody of the synopsis of what we have discussed. The power rule, d dx of x to the power of n. N becomes the coefficient, and the exponent goes down by 1. And direct effect of that is that the derivative of x is 1. If you apply that, you get 1. Constant multiple. The derivative of c times f of x, we are assuming f is a differentiable function. You can take the c out and say c d dx of f of x. The sum rule. In this case, f and g are both differentiable. So the derivative of the sum is the sum of the derivatives. d dx of f of x plus g of x is d dx of f of x plus d dx of g of x. The difference rule says that derivative of the difference is the difference of the derivatives. So d dx of f of x minus g of x is d dx of f of x minus d dx of g of x. And so the derivative of a constant is 0. The derivative of x to the power of n, the power rule, extremely important, nx to the power of n minus 1. The derivative of k times x is k. K is a number, is a constant. The derivative of e to the power of x itself. The derivative of sine x is cosine x. The derivative of cosine x is minus sine x. We had seen this on the first page. The derivative of tan x is secant squared x. The derivative of cotangent x is negative cosecant squared x. The derivative of secant x is secant x tan x. The derivative of cosecant x is minus cosecant x cotangent x. And we will look at this stuff with more details later on, everybody. Okay. I want to look at the proof for the power rule. You're not responsible for that, but I want to do that to remind you of a lot of things. When f of x is x to the power of n, its derivative, d dx of x to the power of n, or f prime of x is n x to the power of minus 1. Okay. So f prime of x is n x to the power of minus 1. You want it? prove that, everybody? Well, there are a few things we need. We are going to go with the definition, the limit of x plus h to the power of n minus x to the power of n over h, because f of x plus h is x plus h to the power of n. So we need to expand that. So I'm going to remind you of factorial. N factorial is n times n minus 1 times n minus 2 all the way to 1, and 0 factorial is 1 because of the definition of a combination. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 100. Just as an example. I remind you of the binomial theorem. A plus b to the power of n is combination of n choose 0, a to the power of n, b to the power of 0. Combination of n choose 1, a to the power of n minus 1, b to the power of 1, all the way to combination of n choose n, a to the power of 0, b to the power of. Notice, the exponents must add up to n. So this is 1, right? This is 1. So this one, see, they add up to n, they add up to n, and so forth. It's a combination of n choose r, n factorial over r factorial times n minus r. Other notations for this one, okay, CNR, NCR. This is used mostly in calculating, or simply NR. Okay, that's a notation. For example, for the binomial theorem class, we all remember a plus b squared, right? A squared plus 2ab plus b squared. That's a binomial theorem. For example, we remember a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. This is also a binomial theorem. But this is n equals 2, n equals 3, and this is in general. As far as the combination is concerned, n choose 0, following the formula, n factorial over 0 factorial, n minus 0 factorial. 0 factorial is 1, n minus 0 is n factorial. They two cancel each other, we get 1. So this number becomes 1. And I'm going to leave it for you to prove n, that means combination of n choose n is also 1. N1 is n, I'm interested in finding this. N factorial over 1 factorial, n minus 1 factorial. The reason bottom is n minus 1 factorial. The top, remember, the n factorial is this. So if I want to stop somewhere, anywhere I want, for example, here, all I have to do is make up a factorial, they cancel each other, and I get n. This is extremely important. So now we are going to expand the expression that we have here, knowing that this number is 1, this number is 1, this number is n. The rest of them are not important, you see 1. So when you expand it, this one becomes 1 x to the power of n, h to the power of 0. The next one becomes n x to the power of n minus 1 h, according to this. The next one, we're going to just write the combination. We are not interested in what it becomes. But notice the sum of these two must be n, and it is. And all the way to the end, the last one, this is 1, this is 1, b to the power of n, h to the power of n, and this one remains. Now, clearly, we can cancel those two and write the rest of them. And when we write the rest of them, we can take the h out. Pay attention how it comes up. When you take the h out from this one, you are left with nx to the power of n minus 1. This one, you get everything now. H squared goes down to h. This one, you subtract 1 from the exponent n minus 2. This one, you subtract 1 from the h. You get n minus 1. Let me clean up my work. And so now this h cancels out this h, and you're left with what we have in the parentheses. limit as h approaches 0 of this expression. This one doesn't have any h, so that is the answer. And then this one has h. This goes to 0, 0. Everything goes to 0 because it involves h, except the first one. And believe it or not, that's the proof. And we are done. Okay, everyone. You're going to? Let's look at simple examples. F of x is x to the power of 6. 6 becomes the coefficient, and the exponent goes down by 6x to the power. You can say f prime of x. Y prime. 1000 becomes the coefficient, and the exponent goes down by 1, becomes 9. We're using the power rule. 4 becomes the coefficient, and the exponent goes down by 1, becomes 4t cubed. However, I like to write not only y prime, also dy dt. Just to remind you, this is a Leibniz's notation, number one. Number two, the independent variable is t. So the advantage of this is that we are telling the reader t is the independent variable, not x. So for example, here we would have written dy dx. So if we wanted to go with the Leibniz's notation, we could have written that. Now, these two. Let me start with the top one. And it's important to know that you can say y prime, that's fine. Or you can say dy dr. And it's 3 times 2 r to the power of 2 minus 1. We get 6r. What I want to mention is various notations, dy dr. ddr of 3r squared, 6r. What about this one? F prime of x equals 10 times 6 x to the power of 6 minus 1, 60x to the power of 5. You don't have to write all those steps, but I just wanted to emphasize how we get that. So to make sure we understand this, we're going to look at this stuff one by one. So we want f prime of x. So there are several terms, one by one. This is 8, and then the exponent goes down by 1, 8x to the power of 7. This one, let me just write it and then I stop writing. For this one, I would say 12 times 5 x to the power of 5 minus 1. That means 60x to the power of 5. Minus the product of these two is 16x to the power of 3. Plus the product of these two is 30x squared. This gives you minus 6. Any constant is 0, so minus 6, and we are done. We had done this with the definition in the previous section. The derivative is simply 5 now, using the fact that the derivative of k times x is k, just a constant. Of course, plus 1 gives you 0. Now, here's the importance of algebra. To use the power rule, we are going to rewrite this as 2 to the power of x minus 1, which means we should be familiar with all of these exponential rules. More specifically, I'm interested in the negative exponential rule. That means if you have a to the power of minus n, you can take it down and write it 1 a to the power of n, change the exponent to positive or negative. If it's negative up there, bring it up. So you can move this up and make it negative 2 x to the power of negative 1. So we are looking at all the rules that we need from the exponential rules. Specifically, we are looking at negative exponential rules. Just reminding you of that. And so if I want to differentiate this, I get f prime of x is 2 and the negative 1, x to the power of minus 1, subtract 1 more, you get minus 2, x to the power of minus 2. You use the negative exponential rule. You take x to the power of minus 2 down. In fact, you're using this one. And you put it back in the proper format. You're done. This one, very simple. 7 times 2, 14 x to the power of 2 minus 1, simply 14x, and we're done. F of x is x times square root of x plus 5 minus 2. To differentiate that, first we are going to change square root of x to x to the power of 1 half. Next, we use the power rule here. The exponent here is 1. The exponent here is 1 half. So it's x to the power of 1 plus 1 half. So the product of these two gives you x to the power of 1 plus 1 half. That means x to the power of 3 halves, 5x minus 2. So a lot of exponential rules. I'm sure you're very comfortable. So we want to differentiate. Now we are ready. We say f prime of x is, we put the 3 halves in front, x to the power of 3 halves minus 1. Let me just write this piece. So this one, when we want to differentiate, we say 3 halves, x to the power of 3 halves minus 1, which makes it 1 half. So this is 3 halves x to the power of 1 half plus 5. Of course, negative 2 gives you 0. Now you change this to the same format. Remember this, square root. So 3 halves square root of x plus 5. What is the derivative of pi squared? Again, what I want you to notice, doesn't matter what we wrote here, pi squared, pi cubed, e 1.5, 2000, 1/3, 2.1. This is a constant. This is a number. This is a constant. That's all you need to notice. And the answer is 0. So I could have e or e cubed or 1 over. If I said, for example, just let's make something up. If I said, what is d dx of 1 over e? It's just a number. Okay? Same answer. So if I give you a number, the derivative is 0 in any format, rational, irrational, you name it. Now, everything in this page requires algebra first, and then we do calculus. So again, I'm reminding you of exponential rules. To differentiate the first one, we change it to x to the power minus 5. Now I'm going to write f prime is equal to minus 5, x to the power of minus 5, subtract 1, which is minus 5, x to the power minus 6, which is minus 5, x to the power of 6. So rewriting it in a format that makes it possible to use the power. What happens in part B? We're going to move this up, and now we are ready to use the power. So we are going to write f prime or f prime of x. We should write f prime of x. It's 2 over 7 times negative 3 x to the power of minus 3 subtract 1. And again, this is it. This is the calculus step. And before we move on, we just had one step of algebra, and now we have more steps of algebra. Over here, this was calculus, and we had algebra and 2 more. So this one we are going to write minus 6 over 7 x to the power of minus 4 down minus 6 over 7 x to the power of 4 algebra. Okay. To do this, we are going to go with algebra again, which means this is x to the power of 5 divided by x to the power of n. Using the quotient rule is you can write it's x to the power of 4 in the denominator or x to the power of minus 4 in the numerator. And that's why we put it in this format, because we are going to use the power rule on that. So that was an algebraic step. F prime is 2 over 9 times negative 4 x to the power minus 4, subtract 1, we get minus 8 over 9 x to the power of minus 4. And now, again, exponential rule, negative exponential rule, take this down, minus 8 over 9 x to the power of 5, and you're done. It's that simple. Again, we want to use the power rule the way it's given. We can't. We have to use our algebraic technique. The first thing is, we've done this before. We change it to x to the power 1/2. And we say f prime of x is 1/2 x to the power of 1/2 minus 1, 1/2 x to the power of negative 1/2, 1 over 2 x to the power of positive 1/2 over 2 squared of x. Notice, again, this was the only calculus step. I can't emphasize this enough. For part E, we are going to use the fact that the nth root of A, okay, to the power of n, you can, okay, you can write them in different formats. So this part is x to the power of 4 over 5. That's the idea. As long as we notice that, we can easily handle it. So we are going to differentiate as follows. Again, that was a calculus step class. So we continue with the differentiation and say f prime is 2 times 4 over 5 x to the power of 4 over 5 minus 1. And this is 8 over 5. Again, let's just box that calculus step. Everything else is algebra. 8 over 5 x to the power of negative 1 over 5. We take it down and we say 8 over 5 x to the power of positive 1, right? And we put it in the same format we received. 8 over 5, the fifth root of x. Okay. And that's done. For part F, later on in the next section, we discuss the product and quotient rules. And some students are familiar with that. If you don't see the easy way out, you may have a hard time with the long way. You can use a quotient rule on this, but it's a long way. You shouldn't, because first you should use your algebraic techniques to simplify. You have a choice. You can make up two fractions, or you may notice that if you factor out the x squared, it works the same way. Okay. And you end up with 10 minus 7x. The reason I showed you two fractions as well, even if this is the square root of x, you write it x to the power of 1/2 and you do it that way. You don't go with the quotient rule. So if you have one term or one algebraic expression at the bottom, because if it's square root of x is not a term, it's not a polynomial. So you divide the top by the bottom and you make up two fractions. And now the derivative is simply -7. You don't have to do much. This is extremely important to know the easy way out, everybody. Find an equation of a tangent line to the graph of this function, f of x equals x squared minus 3x minus 1 at x equals 4. You need two things. You need the pair you plug in. You need the slope. You find f prime and you plug in. F prime is simply 2x minus 3. If you plug in 4 here, you get 4 squared minus 3 times 4 minus 1, and that gives you 3. If you plug in 4 here, 2 times 4 minus 3 is 5. Y minus y1 equals m times x minus x sub 1. So y minus 3 equals m, 5x minus 4. And this is 5x minus 20. You move this plus 3, you get this one. What you need to know is that this pair belongs to the original function and it satisfies that, and it is also part of the tangent line. So when it works out, it means this process was right, has got nothing to do with that. Find the points for which the tangent lines are horizontal. Well, we're talking about the slope of a tangent line being 0 because horizontal lines have slope that are 0. So first we take the derivative, 3x squared minus 6x. And the reason we set it equal to 0 because the slope is given the moment we say horizontal. We factor the 3x out. This is 0, x is 0, this is 0, x equals 2. Make sure you realize that means two different points. So that's why I like to put it in pairs. If I plug in 0 here, I get 5, 0, 5. If I plug in here 2 cubed minus 3 times 2 squared plus 5 is 1. So the second point, the 2 come up. So it's a good practice to put them in pairs. All right, exponential functions. Compute the derivative of an exponential function f of x equals a to the power of x, a general format, using the definition of a derivative, and of course the derivative as the definition, f prime of x is the limit of f of x plus h minus f of x over h as h approaches 0. So using that, then we get a to the power of the limit as h approaches 0 of a to the power of x plus h. And this one is itself a to the power of x over h. So that's what we get. This is a to the power of x times a to the power of h. Remember the exponential rule, the product rule, okay? So the reason we do that, we can factor out a to the power of x. And since the limit applies to h, this can come out. Everything else involving h must remain. This can come out. And now we say f prime of x is a to the power of x. We took it out. Limit of a to the power of h minus 1 over h. So notice something very interesting. F of x is a to the power of x. F prime of x is also a to the power of x times some expression. What if there is a number a such that this expression is 1? Is there an a such that this expression, limit of a to the power of h minus 1 over h as h approaches 0 equals 1? So we experiment with numbers. Numerical analysis, we set h equal to 0.1, 0.01, 0.001, and 0.0001. And we evaluate for number 2, which means when a is 2, this limit is equal to 0.69, or even you can say 0.7, roughly. If we do the same thing for number 3, everybody, again, we're just using one side of h, and we are using this is the closest number, and according to that, this limit seems to be 1.1. But none of them is 1. We were looking for 1. We didn't find it, but for sure 1 must be somewhere in between. And not only that, it's closer to this one. That means it's closer to 3. That's the meaning of it. So we define that definition. E is the number such that this limit, and now we're going to change the a to e, limit of e to the power of h minus 1 over h as h approaches 0. So e is defined as such. Geometrically, this means that of all the possible exponential functions y equals a to the power of x, the function f of x equals e to the power of x is the one whose tangent line at 0, 1, that means the y-intercept, has a slope f prime of 0, that is exactly 1. So this tangent line has a slope of 1 at the y-intercept for the function y equals e to the power of x. Here's the reasoning. We said f of x is a to the power of x, and we said f prime of x is a to the power of x, limit of a to the power of h minus 1 over h as h approaches 0. If you set x equal to 0, a to the power of x becomes 1. And therefore, you don't have to write it. You can write f prime of 0 is 1 times this expression. So limit of a to the power of h minus 1 over h as h approaches 0. In other words, what is f prime of x? F prime of x is a to the power of x times f prime of 0. This is f prime of 0. So f prime of x is f prime of 0 times a to the power of x in general. And so these two definitions comes from algebra. We had it in the beginning. And of course, it means it's not missing. It's just like pi is an irrational number, 2.7182, and it continues indefinitely. And here's the definition we just proved. Is a number such that the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. What do we need to know? When f of x is e to the power of x, f prime of x is equal to that, or the derivative of e to the power of x is this. That's all we need to know. Now, differentiate f of x is given e to the power of x minus x. Find f prime and f double prime. So let's go with f prime of x. Simply put, we know the rules. So e to the power of x is the answer is itself. Minus x is minus 1. So f prime of x is e to the power of x minus 1. What about f double prime? Let's discuss higher order derivatives of f of x. The derivative of a function y equals f of x is itself a function y prime equals f prime of x. Therefore, you can take a derivative of f prime of x referred to as the second derivative of f of x, f double prime of x, or if it looks like an exponent but inside the parentheses 2 of x. Why? I'll explain it in a moment. This differentiation process can be continued to find the third, fourth, and successive derivative of the f of x, known as higher derivatives of f of x. Using the prime notation for derivatives would eventually become somewhat chaotic. Imagine y prime, y double prime, triple prime, and then after that it becomes crazy. We use the numerical notation f, and it seems to be the power, but in the parentheses, when we put it in the parentheses, f to the parentheses n of x, to denote the nth derivative of f of x. So this notation is for that. So for example, this notation means the second derivative, or simply f double prime. F double prime is itself e to the power of x, right? Because minus 1 is 1 e to the power of x is itself. It's that simple. All right. Differentiate where y is sine t plus pi cosine t. So we start with y prime and we start with the first term sine. We know the derivative is cosine, so cosine t. Plus pi, remember pi is a number like plus 5, plus 2, minus 8. So plus pi times cosine. Cosine, the derivative is minus. So plus pi times minus sine gives you negative pi sine t. All right, here, h of t is the fourth root of t minus 4e to the power of t minus cosine t over 2. We want to differentiate this expression. So the very first thing we need to do, we need to write this in a format such that the power rule can be used. We're going to write this t to the power of 1/4. This one, you don't have to change it, but I'm going to change it to negative 1/2 cosine t because I want everybody to see it's some number, negative 1/2 or anything else times cosine t. So in essence, you're differentiating. Starting with that, we are going to write 1/4 sits in front, t to the power of 1/4 minus 1. So that's the first one. The second one, minus 4, e to the power of t is itself. And the last one, minus 1/2 times cosine, the derivative is negative sine. So minus 1/2 times minus sine. And we are going to rewrite this. To rewrite this, I want you to notice that this is negative 3/4. So you can say t to the power of negative 3/4 goes down to the uh, denominator and it becomes t to the power of positive 3/4. And that is the fourth root of t cubed. So first notice this notation, okay, this one. This doesn't change. This one, positive. Now, you can write half of sine t or put it in the same format. I like to put it in the same format. It makes no difference. And again, this one, notice this takes it down, makes it t to the power of positive 3/4, which gives 4th root of t cubed. Example 8, the distance in meters of an object from a starting point is given by s of t equals 2t squared minus 5t plus 4, where t is time in seconds. Part A, what is the velocity of the object from 2 to 4 seconds? Well, anytime you have 2 points in time, it means average. And we had done this question before. So it's being repeated for the purpose of using the easy way out of the differentiation, the next part. So this was done. We plugged in s of 4. So 2 times 4 squared minus 5 times 4 plus 40 minus s of 2, 2 times 2 squared minus 5 times 2 plus 40 over 4 minus 2. And it became 52 minus 38 over 2, which is 14 over 2, which is 7 meters per second. You can find it in your notes. We have done this. Now this part, we want to find the velocity and acceleration of the object. What is the velocity and acceleration of the object after 6 seconds? This one, even if it doesn't say instantaneous, that means instantaneous, especially if you see 1 point in time. So velocity is the derivative of the distance function. All you have to say v of t is s prime. And we did that before, but with the definition, now we're going to take the easy way out. Okay, s prime of t, which makes it 4t minus 5. And this was done, again, previously. Now, the first part for velocity is done. The second part for velocity, you plug in t equals 6, 4 times 6 minus t meters per second. Now, what about acceleration? Now, acceleration by definition is the second derivative of the position function. So a of t is v prime of t is s double prime of t, which means differentiate this expression again, and you get 4 meters per square second. I'm going to discuss the units in a moment. But before I do that, even the next part where it says find the acceleration after 6 seconds, because this is independent of t, when t is 6 or 5 or 4 or 10 makes no difference, it remains at. Why is it meters per square second? I'm going to remind you that this means ds, dt, and the units of distance over units of time results in meters per second, whereas a of t means dv, dt, that means units of the velocity meters per second, over units of time seconds results in meters per square second. Okay, everyone? When does the object reach a velocity of 31 meters? So basically, set the velocity equals 31. Move -5, make it +5, 36 divided by 4, 9 seconds. So in 9 seconds, the object reaches a velocity of 31 meters per second.